Hi everyone, thanks for coming for the next installment of the UCL Dark Invited Speaker Series. Today we're going to hear from Felix Hill on some reasons to do embodied machine learning. Felix is a research scientist at DeepMind, where he works on replicating in artificial systems how we as humans understand and use natural language. His work is at the intersection of natural language processing and understanding and reinforcement learning, particularly focusing on embodied language learning, taking inspiration from cognitive science and psychology. He completed his PhD in computational linguistics at Cambridge University in 2016 in the Natural Language Information and Processing Group, supervised by Anna Kohonen. Really looking forward to your talk, Felix, so take it away.
Thanks, Robert. Yeah, it's really nice to come and give a bit of a presentation, and hopefully it'll be interactive in some sense. So if people have questions, then maybe shout or do whatever you do on Zoom, and I'll try and get to them. And if not, then hopefully there'll be a bit of time, maybe quite a lot of time at the end where we can discuss things. Cool. Yeah. So the motivation for this talk then is that I'm going to try and convince you that it's interesting and important to do embodied machine learning. So just before I start, I should say that when I'm talking about embodied machine learning, I'm, as you'll see, talking about learning in the context of an agent which interacts in its environment. And in all of my work at the moment, at least, this is in a simulated environment. But hopefully a lot of the things I'm going to talk about sort of would naturally extend to the scenario where people were learning in an actual robot, although that's not what I've done and not what I'm going to talk about today. Cool. So I'll start with reason number one for focusing on embodied rather than maybe what we might call classical machine learning. So reason number one, the learning outcomes are different. So for the same model, when learning from a scenario of a static data set, the effects of what that model learns and how it learns to behave once it's trained may be really quite different from an equivalent model when it learns from the perspective of an agent interacting in an environment. So I'm just going to talk about one example here. Lots of people in the context of this supervised learning from static data sets have observed that neural networks aren't very systematic in the way that they generalize. So the idea here is that in the context studied by these researchers, those deep networks don't seem to be very kind of regular or employing sort of rule-like generalization in the same way that adult humans can do. And this point was originally raised by Pinker and Prince in the 80s, and then more recently in the context of bigger modern neural networks by Brendan Lake and Marco Baroni. However, if we consider a really quite simple but embodied neural network learning system, then the veracity of this claim is a lot less clear. So here's a really simple experiment where the agent just has to generalize its knowledge of what a color means and what a shape means and how those two things should go together in reference. So we're going to study this question in two conditions, but to both conditions apply the same set of training instructions and test instructions. So the training instructions are just things like templated instructions along the lines of find a, and then a color, and then a shape, right? So the instruction might be find a blue guitar, or find a red ball, or find a green ladder. And then to measure the agent's ability to sort of systematically generalize this type of instruction grammar, we're going to hold out some combinations of shapes and colors and give those as instructions to the agent and see whether it can successfully follow those instructions as well, right? So in the test episodes where the agent doesn't actually do any learning, it may well receive a instruction like find a red guitar, find a green ball, or find a blue ladder, something like that. Okay, and this test of generalization we're going to consider in two conditions. So in one condition, the agent, we might say, is not embodied. So in fact, it doesn't really make sense to call it an agent. We can think of it as just a visual question answering system, and it's trained via supervised learning. So in this case, it sees two objects in front of it, and it just has to predict which one of those does the instruction pertain to. Now, the instructions are kind of like all randomized, and the locations of the two objects are randomized, but the agent should just be able to look at the two objects in front of it and say either it's the one on the left or the one on the right. So you can imagine that we can train that model using just supervised learning. Then in the other condition, condition B, the agent has to like take some steps, move up to the correct object and bump into the correct object. And that's its way of sort of expressing the fact that that is the object that the instruction refers to. Now, importantly here, the sets of instructions in both conditions are exactly the same in both the training set and the test set. And also the architecture is pretty much the same. There's a small difference because the agent which moves through its environment, each time step takes one of 8 different actions. So at the very final layer, it's like learning a policy over those 8 discrete actions rather than learning a binary choice between 2 different things. So there's a small architectural difference, and there's a difference in the learning algorithm because one of them is a policy gradient algorithm, and the other one is just a classic supervised sort of maximum likelihood algorithm. But the architecture themselves are the same. Okay, and what we observe when we consider the performance on the held out set in these 2 conditions is that there's a much bigger drop-off in generalization performance in the context of the supervised learner than there is in the context of the agent. So this is kind of an interesting observation. There's many ways we might want to think about where the difference comes from here. So in one case, for example, you can imagine that there's actually a lot more training data in terms of visual frames. The agent, as it moves through the environment, is seeing objects from many different angles. And importantly, those objects are getting bigger and bigger in its field of view as it moves towards them. So that's the difference between these 2 conditions. Another way we might think about where this difference comes from is in terms of uncertainty in the network. So if you think about when you give unfamiliar stimulus to the agent, in this case, an unseen instruction, it's not going to be as sure about the right answer as it would be on the training set. And in that case, you know, if you think about the compounding probabilities, the chance of the agent actually manifesting that uncertainty in a mistake, an incorrect classification, that's maybe like greater in the context of a scenario where you just have to take one decision. Whereas if you're predicting a sequence of, I think it's up to like 15 or 20 different actions before, like as a minimum, before you can actually get to the right thing, you might find that as you're getting nearer to it, you're becoming then suddenly like less uncertain, more certain that you're about to make a mistake, and you can recover from that and go and take the actual thing. So there's 2 differences between an embodied learner and a supervised learner, and really makes quite a clear difference here between how well they generalize in this sort of out of distribution recombination manner. Okay, so that was like a really simple introductory experiment. We wanted to make things a little bit more like edging towards a more realistic setting. So in this case, we consider a unity environment where the agents can actually lift up and interact with objects. So hopefully a step in the direction of a scenario like a child or a human who can actually move and interact with the objects in the world around them. So again, we sort of devised a pretty similar test of systematicity, but this time involving interacting with the objects. So in the training set of the agent, we required it to lift up each of the possible objects in the global set of objects that the environment has. So that way, if it can lift them up on demand and not lift up other objects, then that tells us that it kind of like knows what each of the names mean. It knows the reference word for each of the objects in the environment. And then for some subset of those objects in the environment, we also train it to do something with one of those objects. In this case, the only thing that it was kind of easy to implement that the agent could do with an object was to put that object on the bed. So that's what we did. We trained the agent to put half of those objects on the bed. So it knows how to lift all of the objects, and it knows how to put half of them on the bed. And then we just want to measure how well it performs when asked to put the remainder of the objects on the bed, the ones that it wasn't trained to put on the bed. And again, we can set this task up in 2 different interesting conditions to see how well the generalization comes out in those 2 cases, right? So in this case, we were interested in considering the sort of advantages of 3D perspective. So in one case, we have an agent which is in the Unity environment and has a first-person perspective. So as it moves its head, it moves around the world, and it gets that first-person egocentric view of what's going on. And then in another condition, we have a grid world where the agent sees everything in the world from above. And although the agent moves itself, it sees everything, and including itself. So it's really an allocentric perspective. But in both conditions, it's the same number of global objects in the environment. So we matched at the sort of abstract level of defining the structure of the task, we matched all of the different parameters. And again, to the extent where it was possible, we kept the architecture exactly the same in these two cases. The only difference was that in the grid world, there's an action set, like 5 or 6 different actions. So picking up something is just moving left and then up and then right and then up and then going to something, activating a picking up thing. Then putting it on the bed is then dragging that thing step by step back to the location. Here, there's a sort of gray square at the bottom right, and that's the bed. And that's where the agent has to actually go and get the take something to. Whereas obviously in the 3D world, it's much easier for you to see what the agent has to do because you actually kind of like recognize what those objects are. Cool, so 2 conditions. One of them is an allocentric top-down grid world. The other one is a sort of first-person continuous 3D egocentric world. But otherwise, everything else the same. And again, here we notice an interesting difference in the generalization ability of the agent. So the agent trained in the 3D world performs at something like, in this experiment, 75%, say, on the held out objects, so well above chance. And then the agent on the grid world is also above chance, but is substantially lower, right? It's like close to 50%. So there's again a big difference. This was like kind of surprising, although obviously we weren't totally surprised or we wouldn't have done the experiment. But we wanted to understand in a little bit more detail what the important thing was here that was causing the difference. So one thing we really noticed was obviously a big difference here is that in one of these environments, it's a sort of global allocentric view of the world, and in the other one, it's an egocentric perspective. So we kind of met in the middle and tried to make the grid world egocentric as well by putting a little window around the agent such that the actual environment now moves with the agent. Like some of these sort of top-down Atari-style games, the environment will move with the agent, so the agent always stays in the middle of its world. And in that condition, so of course, doing that introduces a type of invariance into the environment, which didn't exist before. If you think about it, there's a number of states in this environment now, which will look identical to the agent, but won't actually be identical states in the environment. And there's also some sort of commonality with respect to the visual field of the agent. There's a lot more consistency there. And what we found was by doing this, we were able to recover almost all of the difference in generalization performance between the original 2D allocentric grid world and the 3D world. So this is some evidence, I think, that important inductive biases in any learning system may come from the physical constraints of having a body, only being in one place, always being in a single place at a single time. These are important constraints which natural learners have. There's other ones as well. For example, as we move our head, the objects that we're looking at, they don't just disappear and appear, they kind of move consistently through time. We get multiple views of the same object. All of these are the sorts of constraints that an animal or any embodied learner is naturally given. And it turns out in this case, at least, that they're somewhat desirable constraints in the sense that they help our system to develop a propensity to generalize in a way that we find convincing. Now, I wouldn't want to say that they generalize better, but they certainly generalize better in a way that, that we find important, and that seems to map onto how we think we should generalize. So I don't know, it's a kind of a whole philosophical question here about perhaps our language and our expectations of how we should generalize are actually determined by the fact that we as natural humans have this egocentric perspective. So it led us to think about the world in that particular way. So maybe it's just the fact that this simulation of an embodied agent is slightly more like the biological system, which gave rise to natural language and these ways of thinking about generalization that can actually, so it's that alignment that's maybe the desirable thing here. That's what I want to propose. Cool. So that's kind of about the spatial consequences of being an agent. But there's also these important temporal consequences of being an agent. Essentially, memory is much harder if you're an agent than if someone's just giving you examples. But I think it's harder in a useful way. So that's what I'm going to try and tell you about now. Cool. So memory, being a learner that's just in one place at one time, I think that gives you like a really unique perspective, a sort of lifelong temporarily egocentric perspective on the world. And I think that will actually create important opportunities for learners and important opportunities for things like meta learning that might kind of not be there in a situation where we just gather all the data from the internet, try and learn from it in that way. Cool. So here's a real life example of impressive memory and possibly meta learning in a real life embodied learner. Let me see if we got some sound.
Name. Wow, it's the Toma. Do you see? Look, it's the Toma. Both researchers are looking at and pointing to the object when Ashley says the name. Look, where's the Toma? Can you get the Toma? Then Max is asked to pick out the Toma. Good job! You found the Toma! Yay! Good.
Okay, so you get the idea. This is called, this is a classic experiment from human language development called the Dax Task. And it's used to identify a skill which children develop at a certain age called fast mapping, which is what you saw there, where an unfamiliar you can get an unfamiliar object and an unfamiliar name and kind of like put them together in your mind such that if you're asked to use that new word in the time immediately preceding that, you can recover that information and recognize the new objects. So children can do that. Turns out that actually certain dogs can do that.
All right, but I have a question about that experiment. Do they also name the other object on the table as a control and then verify that they're doing the fast binding? It's not clear from that video.
Yeah. So my guess is that they do. I mean, so this paradigm is actually used in maybe certainly hundreds of studies since the original one, and I'm guessing that that's like the sort of thing the reviewers would have insisted on. Yeah. So, but I'll tell you about
but far more egregious violations of good control protocols have been done in science and then built upon. So, but anyway.
Exactly. Yeah. No. But that's very true. And but I imagine that has been dealt with. But I'll tell you about my experiments, and then you can also see if I controlled for effectively as well. So. Cool. Yeah. So interestingly, dogs can do it, but not all dogs. Only border collies, or at least only discovered in border collies. So anyway, some dogs can do it. Young humans can all do it. We were interested in seeing what it would take to have an agent do something like this. So we kind of, this is where the controls in our experiment we can certainly scrutinize. This is where we tried to build a sort of synthetic, simulated version of what you've seen there. So we separated the environment training episodes into two phases. I'm going to call it the presentation phase. And in the presentation phase, the agent goes around the world and learns the name of all the objects. So this is kind of the analog of a human presenting objects to people and then telling them the names of those objects. But the agent just goes up to an object, and then the environment knows when the agent's facing it and releases the name of that object. And then at a certain point, either when a time limit is met or when the agent has visited all of the objects, the environment transitions to the instruction phase. And that involves randomly shuffling the location of the agent, all of the objects. So the agent can't rely on like the absolute location of things in its memory. And the agent receives an instruction, which is one of the names of the objects that was given in the presentation phase. And the agent then just has to go up to the object and pick that thing up. If it picks up anything else, it fails. So we know that it's not like universally picking up all the objects and succeeding that way. And then, of course, the most important detail about this task is that the binding between the objects and their names, it does not persist after this total process is finished, right? So there's nonsense words like Dax and Blicket, and they correspond to different things in each episode that the agent learns. Otherwise, this would just be a classic sort of a classic long, slow language learning episode. And it wouldn't be too surprising that the agent could learn that. Cool. So yeah, if you want to just get a sense of what this ends up looking like, this is the agent learning the name of that thing, and that thing. So we had to go onto a website called like www.sillywords.com or something like that to get all these words. It's interesting, actually. They're sort of like phonetically plausible English words, or phonologically plausible English words, even though they don't actually mean anything. And that's actually really important for getting like human performance on these tasks. If you make these words not phonologically plausible, humans do much worse than if you make them phonologically plausible. So tells you something about human memory. Cool. So anyway, what sort of agent could learn to do a task like this? Well, the default agent we use, which is probably the one we used in the previous experiments, is really about as simple as you could imagine in this sort of setting. So the agent receives at every time step observations from a language channel and visual pixel observations. So it has to embed those. So we use a small visual network and a small language network to embed them. And then we just concatenate those and merge them together through a connected layer into a sort of multimodal code representing the input at every time step, which is passed to an agent memory core. The default here is a recurrent LSTM agent memory, and then the output of that every time step determines the actions that the agent takes. Okay, now I'll spoil the story by telling you that didn't learn this task very well. There's many, so in theory, an LSTM should be able to learn this task, right? The information that the agent needs is at the start of the episode, and it just needs to be able to retain that information to the point where it makes the final decision about which object to pick up. The problem is what you actually need in this task is like really quite a clear sort of high bandwidth resolution view of what an object used to look like in the past. And it's probably quite hard for an LSTM memory to kind of compress that quite high bandwidth information into the state of the LSTM, and for it to learn to kind of retain that information and then recover it. Obviously, people know that recurrent networks have difficulty, even with LSTM gates, retaining long-term dependencies, and in particular, if the dependency is between what the world looks like now and matching it with a clear memory of what it used to look like in the past. That's actually pretty hard for an LSTM architecture to learn. So our first attempt to overcome this involved, the classic solution to a problem like that, which was an episodic style memory buffer. So in this case, again, the visual and the language codes are merged together into a multimodal code and placed into a memory buffer. And the idea here is that the agent can sort of consult that memory buffer at any time step. So those things just unilaterally kind of just go straight into the memory buffer at every time step. And then at any time step the agent needs to make a decision, it can sort of consult more directly back to its past. And it does that by learning to produce a query, and then that query matching all of the memories in the past, and the top matches are returned back to the agent in order for it to be able to potentially use that information to take a decision at the current time step. So this effectively like cuts the path of the gradients between the present and the past, and in particular allows it to access this quite literal verbatim kind of representation of what the world looked like at some time step in the past.
So can you clarify, what about like the experimental protocol? So what are all these other multimodal codes in there? Because if you're just primarily seeing, if I've seen an image and a word and I need to do fast association, the simplest thing without using a DNC would just be present the image and the word to the RNN at each time step and let the recurrent network just deal with whatever non-Markovness there is in the environment.
Yeah. So I guess that's here, right? So okay, the multimodal code here is like there could be a connected layer which merges them together, but they could also just be concatenated, right? So and then they could be that could literally be the input to the recurrent network at every step.
Right.
So
yeah.
Let's consider those the same thing.
But what in your next illustration, you talk about several multimodal codes. Is there, and I didn't get that from the experimental setup, is there a scenario where there are several words and images associated, but some of them might not be relevant?
Yeah, so maybe this diagram's a little misleading. So I guess because of the next slide, I'm just emphasizing the fact that when a representation here plausibly includes information from the visual stream and from the language stream, I'm just flagging that up. Yeah, these things that say multimodal code here, they are plausibly a combination of the vision and the language input at from any time step in the past throughout the episode. And in particular, when I return K of them, they're actually pooled in a certain way. So in that sense, that becomes almost like an average of the top K matches going back in the past combined together. So I guess I'm just flagging up which of these parts of the network contains information that may have come from the visual or the language stream, and which contains information that may have come from a mix of both of those. And in this case, everything that's dark blue is like a mix, plausibly a mix of both. Anyway, maybe it'll be a bit clearer when I get to the next slide. So yeah, so we sort of made a modification to that DNC in a way, because again, that wasn't working too well. So notice this memory here in the classical DNC is kind of content addressable, right? I've got a query, and then I'm going to just take an inner product of that query with the content of the memory in order to see where the match is, and then return the content. So now obviously with things like transformers, key value memories are becoming more commonplace. So one modification we made to the DNC was that, you know, we turned it into a key value memory, but also the important insight in this architecture is that we also just in the context of a key value memory, we are also keeping the modalities separate. So in particular, we can set it up such that in our memory, the keys of the memory are represented by one modality, the values contain the information from another modality, and then when we make a query, that query can come from the modality corresponding, in this case, to the keys. So that's what we do. And you can see why that might help in this task, right? Because if I'm asked to pick up a Dax, one thing I want to do, right, is go back into the past and think, when did I hear the word Dax before? And then at that point, I just try and think, okay, what was I looking at the same time? So it allows me to do that. So I'm searching my memory just in one modality rather than in the combination of the two. And of course, this is an asymmetric setting because I'm querying according to language and I'm returning values according to vision. But you could also do the opposite thing and plausibly have the best of both worlds. So in a scenario where I needed to actually produce some language to solve the task, that separation would be useful, but the converse way around. Okay, so that's how this architecture works, right? It's super simple. It's kind of tailored to the nature of the task, but I think that the insights that come from separating the modalities in memory in this way could plausibly translate to many other tasks. So yeah, it's really as simple as that. It's like a DNC, but we have a key value memory instead of a content addressable memory. What the values of the memory are just everything we saw at a particular time step of the past, and the keys of the memory are what the language that I was listening to or the sounds I was hearing, you could imagine, at that time in the past as well. So one job of the memory is to retain the alignment between the two. So things that are at the same time step are stored in the same row of the memory. So then in this case, when the agent gets the instruction, pick up the Dax, what it has to do is just look back over all of the keys of its memory, which is all of the words it's ever heard in the past, match the current instruction, which is pick up a Dax, to what it heard in the past. Now, the closest match will probably be this is a Dax, which was something it would have heard in the past. So then it just returns into the forefront of its mind what it was looking at when it heard that. Hopefully that'll be a representation of the object, which is the Dax. And then the agent just needs to look at what it's currently looking at and ask itself, do these two things match? And if they do, it can move forward and take the thing with some confidence, right? Cool. One thing I want to add, though, is that some semi-supervised learning actually made a huge difference as well. So this sort of architecture, I think, can struggle to be trained, right? It can be hard to train it because there's sparse rewards at the end of episodes. There's not many gradients for actually learning to represent the relatively high bandwidth input, like the visual input, with enough good quality features such that the whole system that I just described can actually work. And it turns out that any sort of tricks of semi-supervised learning can really help this, right? So we just did something really simple, which was to reconstruct from the core state of the LSTM, the input at that time step. But, you know, anything more fancy, like any of the sort of learning to match obscured or shuffled views of an image, and those sorts of techniques could probably be even more effective here. Cool. So what we found then was that yeah, the DNC-based architecture and the LSTM-based architectures. Remember, these are the architectures that kind of merge together the vision and the language features together into a multimodal representation in memory. They were not so effective at picking up this task. But in the dual coding episodic memory, which is the one that keeps the features of the visual features and the language features separate, and also in a transformer XL memory, the agent was able to learn this task pretty effectively. Notice that in a transformer XL memory, we're also just concatenating the vision and the language and passing them then to the self-attention layers. So it can also kind of learn to, I think, more easily learn to keep the vision and the language separately and do something like what is almost hard-coded into the dual coding episodic memory I described, which is to look up in the past conditioned on one modality and return the values of the other. Cool. So once we've trained the agent, we're interested in, like, not only can we train it to solve this sort of task, but also how does it generalize that knowledge? So one interesting thing is that if you train it to do the task with 3 objects, it can generalize above chance to actually solving the task with 5 objects and 5 nonsense names. But its performance does drop off. So that's the red line you see here. But if you train it to do the task with 5 objects and then evaluate it on 8 objects, its performance doesn't drop off that much. So that kind of suggests to me that at some point it learns a less it's less overfit to the number of objects, and instead it's learning a generic strategy to explore the world, pick up all the names, and then retain them, sort of write them into memory in some sort of manner which is agnostic to the actual total number of objects. So it's kind of learning an algorithm, a memory algorithm for solving this task, rather than a less abstract solution to the task. And another nice thing about this agent was that it's actually able to apply its ability to bind these unfamiliar names to objects that it's never seen before. So this tells us that its visual system is sufficiently developed in order to bind nonsense names to anything new that it ever sees, regardless of whether it's ever seen that before in training. So to show this, we separated the world into a training set of objects, which we used to sort of have the agent initially acquire the task. And then we just held out some separate objects that are just not involved in any of that training and evaluated how well it did binding words like Dax and Blicket to those objects. And it does pretty well, right? So it's almost at 90% on those held out objects. But its success here does depend on the total number of objects in the training object set. So in the special case where there's only 3 objects in the training object set, that means every training episode involves exactly the same physical object. That doesn't give it enough generality in its visual system to then be able to generalize this to new objects. But if that number goes up to 5 or to 20, then then the important thing here is that the agent can distinguish different objects that are different. It doesn't need to recognize the object. It doesn't need to know what they are. It just needs to be able to distinguish differences in objects. And when you involve more than 5 objects in its overall training experience, it seems to be able to develop the features to do that. Another important thing is that if you allow it to retrieve, you can vary the number of steps that you allow it to retrieve from the past in order to make a decision about whether it's the right object. And actually, it gets slightly better if you increase that above 1. So, in theory, you could imagine that you only need 1 snapshot from the past to solve this task, because I just need 1 photograph from my previous memory of what a DAX is, and then I can do it. But actually, if you can retrieve more than 1 time step from the past, you actually learn a more robust policy for solving this. And in particular, your ability to do this for held out objects goes up. So, there's some story here about the fact that as a embodied agent which sees the world over time and gets multiple views of each stimuli, that actually is valuable for forming a sense of what things are, what objects are different, and building representations of those objects. Cool. Now, what else? Another classic human study is actually done to show that it's not just that specific object that babies are binding the word Dax to, but it's the whole category of things that look a bit like that object. So we wanted to evaluate whether the agent could learn to do that sort of category generalization, where it's binding the word Dax to a particular category rather than a specific object. And to evaluate that, we change the DAXes halfway through the episode, right? So we show it an example of one type of teddy bear and say this is a DAX, and then we change the teddy bear. Maybe we change the color or just change something about it. And we evaluate whether or not it can still pick up the teddy bear when it's instructed to pick up the DAX. So to enable that, we use ShapeNet, which is a set of 3D objects that's also got this category structure, a little bit like WordNet or ImageNet. So to train we trained this in 2 conditions. So in one condition, during training, the DAXes that the agent was presented with and the DAXes it needed to then go and find were identical. So there was no shift in the category. There was just a single example of a teddy bear, a single example of a horse in every episode. And if we trained it like that, it then wasn't very good at test time at extending unfamiliar categories. But if we trained it to extend categories, so if we, when showing it how to do the task, we gave it an example of a horse, then we said pick up a horse and it had to pick up a different horse, then it could kind of meta learn the ability to extend these categories. And then at test time, when we had a held out set of categories, it was actually able to extend those categories, over 80% accuracy. Cool. And then the final thing, which I think is very pertinent to models like GPT-3. So this sort of fast language learning is obviously something that these enormous text-based language models can also do, which is somewhat surprising, or was somewhat surprising before everyone discovered it. And this is one example from the GPT-3 paper. So to do a fardaddle means to jump up and down really fast. An example of a sentence that uses the word fardaddle is, so you're defining the word to the pre-trained language model. And it can respond in a way that indicates that it now knows what the word means, right? So it says, one day when I was playing tag with my little sister, she got really excited and she started doing these crazy fardaddles. So importantly here, we can think of its knowledge of the word fardaddle as fast lexical knowledge. That's new knowledge that is just acquired from the prompt. but then its knowledge of all the other words in its output we can think of it as more like slow lexical knowledge, in the sense that it's picked up the meaning of those words from the enormous amount of training it had on an enormous text corpus. So yeah, in our embodied, so of course, thinking about this example and then the agent I've just described, there are some differences. We train ours, like explicitly encourage it to do this meta learning by giving it many, many hundreds of thousands of episodes of Dax tasks and training it to do that. The interesting thing about a language model, of course, is that nobody's really training it to do the meta learning. They're just training it to predict the next word. And this is a kind of emergent phenomenon as a consequence of predicting the next word. So there's an important difference. But anyway, we wanted to see whether or not this ability to combine long-standing fixed lexical knowledge with newly acquired fast lexical knowledge in that sort of seamless way was also something that our agent could exhibit. So to do that, we needed to introduce some words that weren't Dax or Blicket, but were instead actual real things that mean the same thing in every episode. So we pulled out the bed again and the tray. So now the agent gets, firstly, the first part of the episode, the agent gets told the meaning of some new objects it's never seen before, potentially. And then in the second half of the episode, it gets asked to put one of them on either the bed or the tray, according to the name that it's recently picked up. So in following the instruction, like put the Blicket on the bed, it's hopefully integrating its long-standing lexical knowledge of what a bed is, which it's acquired over many episodes, and the fast semantic knowledge of what a Blicket is, which is only just acquired in this episode. And yeah, eventually we kind of got away, we managed to train an agent to do this. So here you can see it slowly visits these three objects, gets a nonsense name for each of them. That's the instruction phase. And then in the second half of the episode, it's asked to do something with one of them. So put the thing on this Montinsia on the storage tray. I think, if I remember correctly, it's that cube is what it corresponds to, and then eventually it does put it on the storage tray. So it can kind of do the same thing as GPT-3 in some sense, which is to integrate the long-standing meaning of what a bed is or what a tray is with the newly acquired meaning of what these nonsense words refer to. Cool, okay. I'll quickly give you a couple more reasons to do embodied machine learning, but they're very related to the previous one. So one of them is that if you do embodied learning or study any problems in the context of an agent, you face exploration problems. That's quite boring in some contexts, but it's also interesting. And much like the problem of memory being harder, it's an opportunity because exploration and cognition are actually related. So hopefully this example will give you one reason to believe that. So I might not have mentioned, but in actual fact, in a lot of the experiments I just described, we gave a small shaping reward to the agent to motivate it to find the name of each of the words. Because the credit assignment problem of like going up to something, getting its name in case it needs that name later in the episode is like a little bit too hard for our RL algorithms to solve. So we gave it this small shaping reward for learning the names of everything, and then a bigger reward if it got the right thing at the end of the episode. But it turns out that we don't actually need to give it the shaping reward if we use some sort of methods for intrinsic motivation. So I don't know if you're familiar with this literature, but there's a whole body of literature on non-parametric or semi-parametric approaches to stimulating an agent to explore its environment without there being actually rewards for doing so. And a lot of them fall into this family of like information theoretic measures, where essentially the goal is to visit states that, according to your memory, are novel. So there's an algorithm from DeepMind called Never Give Up, where the network learns to embed its environment into observations that go into a memory, and then essentially it rewards itself for finding any states that are quite different from that set of states which is already put in its memory. So we just took that algorithm out of the box, but we were interested in motivating the dual-coding episodic memory that we had in our fast language learning agent. So we just applied the same algorithm, but remember here we've now got a memory which is a key-value memory, where the information in the language modality is expressly represented in the keys, and the information in the visual modality is expressly is in a different column of the memory, which corresponds to the values. So by keeping the information from the different modalities separate, we can apply this intrinsic motivation process separately to both modalities. So we can then start to motivate the agent to find states which are novel, not in general, but in specifically novel with respect to language, or specifically novel with respect to vision. And of course, both of the data coming in from these two modalities, the distribution of that data is radically different, right? Language is like short and sharp. It's not always there. If someone screams, we really ought to remember that. Whereas we can always see something, so the notion of an important visual event is much more subtle and harder perhaps to tease out of raw data. So yeah, you can probably guess where this is going, but essentially we just showed that it's possible to apply this same algorithm only on the two modalities when separated, and that's actually much more effective than when applying them on the data as merged together in the agent. And you must be able to think why. It's basically the fact that if I'm motivated to get to states where the language in particular is novel, then in this particular task at least, I'm basically going to be motivated to go visit all the objects, because it's only when I see the object that somebody tells me that's the name of the object. It's only when I'm looking at an object that the language channel actually is activated. So it's kind of a consequence of the task that we built, but you can maybe at least see how it could correspond to a more ecologically valid idea about using the distribution of language in the world to your advantage, because it's not always there. So when it is there, it's probably worth remembering that. And yeah, here you can see that an agent which is motivated to explore based on finding merged visual and language states in the environment doesn't actually pick up the task. But if it's motivated separately to get a bit of reward for finding novel linguistic states and a bit of reward for finding novel visual states, it does pick up this task. And so we can do away with those shaping rewards and still solve the task. Cool. And as a final point, it's a bit of a nod to some work I did with Ed many years ago, but a really important one, I think, is when you work with an agent, and it's true if you work in generative models of vision or generative models of language to some extent as well, but you kind of can't take shelter in the solace of supervised learning with like nice labeled categories, right? And I think a huge number of important problems in language and simulation of behavior don't have a nice set of labeled categories where you can say, okay, we're going to evaluate that. That's how well we're doing. Great. Okay, evaluating behavior is much harder than that, but it's also like maybe more rewarding and maybe more interesting because of it. So here's a classic example that we used to talk about for instruction following. Imagine you wanted to train a system to do these things. Forget the difficulty of actually training the system to do these things. How would you know that the system has done them? How would you evaluate this? How would you reward the system for doing these things, right? Even things like put the bike behind the house and put the domino behind the pencil. I mean, just think about that, right? If you put the domino 1 meter behind the pencil, that's probably not succeeding, right? But if you put the bike 1 meter behind the house, that's probably okay, right? So even like something as innocuous as putting something behind something is incredibly subjective, and it almost requires a full understanding of language in order to be able to evaluate this stuff. Yeah, and you could argue certainly that like evaluating these sorts of things and instrumenting a procedure for evaluating these sort of things is equally difficult, and certainly as futile as it would be to instrument a procedure to like to say whether or not there was a dog in an image, or to or to write a procedure which could generate a picture of a cat or something like that, right? It's really not easy, and we know that those problems aren't easy, and that's why we try and learn them from data. So that's what we tried to do in a really small way with this work, Agile, which Ed was involved in quite a few years ago now. And the insight here is just that for even quite simple instructions like put the things in a circle, actually you'll see that in this grid world we could have written functions to check whether or not these things were done correctly. But the whole point was that we didn't, because in the general case, it's not tractable to do that. So instead, we had an algorithm, Agile, which jointly learned a policy for evaluating a policy. So basically a reward model and a forward RL model together. And this is an adversarial process where basically the forward RL model is rewarded to the extent where the inverse model can't tell the difference between it and like some well-trained guide. And then so since then we've scaled this up a little bit, and now we get more human demonstrations into our environment in order to do something similar. And importantly, here we can now do a more conventional method for simulating behavior, which is basically like supervised learning of the actions or behavioral cloning, we can also complement it with a bit of RL, but again, where the reward just comes from a learned reward model, and then try and train this system using an Agile-like method, but also with some behavioral cloning, some just classic supervised learning of the human instruction data. And so, well, how do we get the human demonstrations? Well, we get 2 humans to play in the environment, and we get one of them to set the other a language challenge, and then the other one goes and does the language challenge. And that could involve returning some language, or it could involve just moving around and taking some actions. And then after getting them to do that, we record a record of all that behavior, and then we try and simulate it. So, eventually it's leading to agents which can follow a wider range of instructions in these sorts of environments. And certainly, if we wanted to write reward functions to evaluate all of the different things that this agent can do, it would be an enormous amount of work. It was also an enormous amount of work training an agent to learn these things, but hopefully in the long term, the method will scale to many more situations. And this agent's slowly getting better and better. It can now respond in language, answer some multi-word questions, do various things like along these lines. It's still nowhere near as good as we'd like it to be. It's a difficult problem, but I just wanted to point out that this problem of evaluation in an embodied agent, it's a really critical problem, but I think ultimately it's important to attack that problem head on. Rather than taking solace in, I created like supervised learning data sets for language, like Glue. I worked on Glue and those sorts of problems, and they're fantastic as well. They have a very important role. But ultimately, it's like, ultimately to get to the systems which really convince people they can understand language, the solution is not going to be some labeled language data and a system which can predict those things with high accuracy. I think that's my view on that. Cool. So just to really quickly conclude, I've given 4 high-level reasons to think about doing embodied machine learning as well. And I should say this should not replace classical supervised or semi-supervised or other learning systems which are not in the context of an agent. This is totally complementary, but I think it's important to be doing it alongside that work. So firstly, we've seen that often, even if the architecture is the same, the learning outcomes are different as a consequence of being at a single place in a single time with a body. And in particular, that raises important memory challenges, but there are opportunities. There could be opportunities for meta learning. There could be opportunities for us to get more efficient algorithms where we need to really attend to the past rather than treating everything in the past equally. They also encourage us to take on challenges around exploration, which are actually relevant to the problems of cognition. And of course, the problems of cognition, and in particular, the problems of semantics and knowledge, are very relevant to the problem of exploration. That's kind of like those 2 are different sides of being intelligent to some degree. And certainly also this problem of evaluation, which also is very inherent to language generation in general. It's a really big problem that you come across when you do embodied machine learning. And I think thinking about that problem can lead to techniques and solutions which are really widely relevant and might take machine learning and AI to the next level. Cool. So that's the end of my talk. Here's some people I've worked with, including Ed and Dima, and then a bunch of people who are in DeepMind. Thanks.